This presentation is delivered by the Stanford Center for Professional Development.
There we go. Hey everyone, welcome. I have two handouts for you today. One practice midterm and its cousin, the practice solution. I haven't written our midterm yet, but I'll get to that this weekend. I'm typically very good about imitating the structure of the practice midterm, but I never promise that I will. If I come up with some new idea that I think is fair to test some material, then I go for it. Okay, but all of those problems on the practice midterm are drawn from previous midterms over the past 3 years. It's a little longer, just a hair longer than you're likely to see. Typically it's 2, 3, or 4 questions, depending on how intense any one question is. This one has 5 on it with some short answers. My recommendation, if you can do this, it's difficult to, but if you can take the practice midterm during some 3-hour block and just write it out in full and then grade your own work, that's a much better way than just saying, looking at the midterm, looking at the solution, saying, oh yeah, that's exactly what I would have done, because it isn't. Okay, so try and write out the solutions, and then you'll have to invest some energy in deciding what types of errors are significant, what types of errors are not. I can tell you right now that we're very concerned with the asterisks and the ampersands and the arrows and the dots and the casts. Ultimately, the questions are really just hopefully interesting backstory and vehicles for us testing all of that stuff. And I don't care about the for loops. I don't care about the plus pluses, unless it's point arithmetic. Okay, I really care about the asterisks and the double car star cast and things like that. So don't think that they're going to be viewed as minor errors. They're not, because a car star cast is very different from a car star star cast. You might as well cast it to be a struck triple star. It's just as wrong if it's not correct. So concern yourself with those things. The midterm is a week from tonight. It is in Hewlett 200. That's probably one of the largest lecture halls on campus. It's not in this building, obviously. It's across the street. So there's that. You can take it anytime on Wednesday during some 3-hour block that fits in between 9 a.m. and 5 p.m. if you can't make it that night. You can't start it during lecture hour. If it's best for you to skip lecture hour, that's fine. If at all you can make it that night, it just makes everybody's life easier, because otherwise somebody has to be around to make sure we can answer your questions. We will be around, there's no doubt about it. But don't take it earlier just because it's convenient for you. Please try and take it at night if you at all can. There's something else. I updated the website yesterday, but it didn't make an announcement because another website wasn't updated yet. But immediately after lecture on Friday, a friend and colleague of mine, colleague is such a snotty word, a coworker of mine at Facebook is giving a technology talk in, actually, as it turns out, the same room where your midterm is. So you can practice and get a feel for the room on Friday by going at noon. I saw him give the talk about 3 months ago, and at the time I was watching him give it, I said, this is exactly the type of material, type of talk that helps motivate the beginning 4 weeks of CS 107. He won't talk specifically in terms of realloc and malloc and free and vectors and hash sets, but when he talks about the system that's in place to store the billions and billions of photos that they have, and they need to grant laser-fast access to any particular photo that might need to be served up, that's an incredibly difficult infrastructure problem, and it relies on this very clever indexing scheme in order to go and find a photo somewhere on one of the, I can't say the numbers, n number of servers where photos reside, and it has to do that quickly. And so it's actually concerned with things like minimizing the number of disk reads and things like that. And so very little of it is beyond the scope of what you've learned in the first few weeks of 107. We're also giving you pizza and soda, so if you feel like you're sacrificing lunch, then you're not really, because we're going to be giving you food. If you're all interested in going to that, please RSVP by visiting 107, which leads you to the ACM website. Just RSVP so that we know to get you some pizza. It's not televised, unfortunately, so you actually have to attend something live if you want to go see this. And we can't televise it for I think, obvious reasons. Okay, so there's that. When I left you on Monday, today's Wednesday, when I left you on Monday, I was 5 minutes into an example that I want to use to illustrate how compilation and linking work, and I'm going to actually frame it specifically in terms of GCC. This was the program I wrote. Int main. I really don't care about those arguments, but I do care about this. Void star memory, I'll just write mem this time, is equal to malloc of 400. I want to assert in the style that we're used to, mem is not equal to null. I want to print yay \m. I want to dispose of the memory. And I want to return 0. I'm only allowed to call malloc and free without running into any issues. If I go ahead and pound include std lib.h, there's a D right there. I only can call printf cleanly if I pound include that right there, and the assert macro is available to me via this header file. This is the entire program, save for the implementation of malloc and printf and free, which resides in standard C libraries. If I compile this, and I just do gcc, whatever this file is named, it can be made to generate two things. It can be made to generate a .o file, and it can be further made to generate an executable. Based on the way this is set up right here, you wouldn't be surprised that there's a call to malloc instruction somewhere inside there, that there's a call to printf, that there is a call to the free function, that eventually there's an rv is equal to 0, and there's a return. There's actually an sp is equal to sp minus 4 up top. There's the corresponding sp is equal to sp plus 4 right there. Those things should be make sense to you because you know what happens in response to local variable declarations and return values and function calls. Okay? That makes sense to people? If I were to compile this, even though it's not a very interesting program, I compile it, it generates this assembly code. This is just compilation. This is linking. By default, even if you just have one .o file, what linking really is it's the blending and merging of this .o file and any other ones you have, but in this case we only have one, the .o file with all of the standard libraries and the standard .o files that come with the compiler. The standard compilers have the .o code for printf and malloc and free and things like that. It basically does what is necessary. It stacks all of them on top of one another to build one big executable. It usually splices out everything that's not touched and not needed, but it includes the code for any function that might come up during execution. Okay? It has to be able to jump anywhere possible while a program is running. Because this is set up the way it is, it'll compile cleanly, it'll run, it'll print yay. As side effects, without really making too much noise, it'll allocate a buffer of 400 bytes, make sure that it succeeded, and then free it and return 0. It's just this very quick program to really print yay, but to also exercise malloc and free and confirm that those things are working. Okay? What I want to do is I want to see what happens if I comment out this right there. Let's give you some insight as to how little, what little impact the .h file has on compilation and linking. If you were to say that this would generate compiler errors because it doesn't know about this printf function, you would be right for some compilers. Okay? As a result of commenting that line out there, you know enough to know that the translation unit that's built during preprocessing won't make any mention whatsoever of printf. Okay? So when time comes to actually check to see whether or not printf is being called correctly, it doesn't have the information it normally has. Okay? Most compilers, many compilers would be like, whoa, what are you doing? I've never heard of this function. I don't like calling functions that I don't see prototypes for, and some might issue an error. GCC does not. We'll talk about printf in a little bit more, but if during compilation it sees what appears to be a function call, what it'll do is it'll just infer the prototype based on the call. Does that make sense to people? Okay. It sees that a single string is being passed in here. Compilation would issue a warning saying no prototype for printf found, but it doesn't block you from compiling, and it still would generate a .o file. We are calling it correctly, as it turns out. Okay. as long as you pass in at least one string, printf is able to do the job. And if there's no placeholders in here, so it's not going to have any problems executing. By default, when GCC infers a prototype, it always infers a return type of int. Turns out that that is the real return value of printf. We normally ignore it, but the return value is always equal to the number of placeholders that are successfully matched to. This particular call would return 0, but I'm not concerned about the actual return value. I'm concerned about the return type. It happens to match up with what's inferred by the GCC compiler. Does that make sense to people? Now, if several other printf calls were to appear after this one, they would all have to actually take exactly one argument, because it's inferred a prototype that's actually slightly different than the one that really is in place. Okay? Does that make sense to people? So you may say, okay, it's going to compile here. What is the .o file going to look like? It's going to look exactly the same. The .h file just consolidates data structure definitions and prototypes. There's no code emitted on its behalf. All it does is it kind of trains the compiler to know what's syntactically okay and what's syntactically not okay. Okay? Make sense? But as it infers this prototype, it's one slight hiccup in the form of a warning during compilation, but it still does sp is equal to sp minus 4. It still copies to m of sp the address of this capital Y. It still calls printf, and it technically expects rv to be populated with the return value, although this happens to ignore it. Okay? You generate this, and I'd say more than half of the students assume that when you link to try and build this executable, that somehow it's going to break down because it doesn't know that printf should somehow be included. Do you understand why people might think that? Yes? Every time you try to build an executable using the GCC system, technically you're using a GCC, but you're using a cousin of it called LD, which is just for load. For link. It always goes and searches against the standard libraries, whether or not there were warnings during compilation or not. Printf sits as a code block in all of those standard libraries, so it happens to be present during the link phase, even though we never saw the prototype for it. The presence of a pound include has nothing to do and makes no guarantee about whether or not the implementation of any functions defined in that thing are available at link time. If something's defined in the standard library set, it's always available, whether or not we behave with the prototypes. Okay? Does that make sense to people? Okay. If I bring this back and I comment this out, then it doesn't have official prototypes for malloc or free. So as it comes down here, it doesn't even see that line. It expands this to a bunch of prototypes and data definitions, expands this to at least the definition for assert. It's fine with that, looks at this as, well, I have no idea what malloc is. We're calling this like a function, so I'm going to assume it's a function. I'm inferring its prototype to be something that takes an int and returns an int. It does not actually look how it's being used in the assignment statement to decide what the return type is. So it'll issue 2 warnings in response to this line. It's inferring the prototype, and then you're assigning a pointer to be equal to a bona fide, what's supposed to be a plain old integer. Okay? There are no problems with this because it sees the definition of assert. Printf is fine. It looks at this right here, and it doesn't like this line either because it hasn't seen a prototype. It infers one. It issues a warning saying it's inferring a prototype for free. It assumes it takes a void star. It assumes it returns an int, which is not true, but we're not looking for a return value, so it's not a problem. Okay? And then comes down here. So this would also generate the same exact .o file. It would issue 3 warnings. Okay? 2 for missing prototypes and 1 for incompatibility between L value and assigned value. But it would create this, and when we link it, it's completely lost memory. There's no record in here that some .h wasn't around and that there were warnings. Okay? It just says that there's a little bit of risk in what's happening here, but I generated it because this as a .o file is consistent with the way you wrote the code here. Okay? Make sense? Okay. So it goes on and links, and when we run this, it runs beautifully. If I comment these 2 lines out, then I get a total of 4 warnings. But it still generates the same .o, and it generates the a.out file that still runs. Yep?
Right. I didn't understand why you said it runs beautifully. It somehow understands malloc and free even though the .h files aren't there.
It does run beautifully. The question is, he doesn't understand why it runs beautifully. All this does is it tells the compiler what the prototypes are. There's no information in .h files about where the code lives. The link phase is responsible for going and using the finding the standard libraries. That's where malloc and free and printf are defined. It's not as if there are hooks that are planted in the .o file because of what the pound includes used to be. As long as this and that are in there, and they will be, whether it's the result of a clean compilation or one with 3 or 4 warnings, it'll still have these. And so when we link this against the standard library set, it'll try and patch these against these 3 things against the same symbols that exist in the .o files, and it'll create the executable. Does that make sense? Okay. That's a different problem, but that isn't the case here. Okay, I haven't defined my own printf or my own free. Okay. If I comment these 2 things out, then I get all the warnings that I've talked about so far. If I bring them back, I have a clean compilation again. If I comment this out, we have a completely different scenario. If it doesn't see any mention of how assert is introduced as a symbol to the compilation unit, comes down here, says, I know what malloc is. It's a function that takes a size t and returns a void star. Okay? Comes here, it's like, I don't know what assert is. So look at it. If I didn't tell you what assert was 2 days ago, or I guess, yeah, 2 days ago, you would say, oh, that must be a function that takes a Boolean and returns a void. Okay? Well, we know that it really isn't that because we know that how it's officially defined in assert.h. But because this has been commented out, it looks at this. It's not like the word assert is hard-coded into the compiler. It actually assumes that this is a function call. This would now appear in the .o file. Does that make sense to people? Yes, no? Okay. Would compile fine, would compile fine, would compile fine. Generates this. The link phase would actually fail. And the reason it would fail is because even though there's code for printf and malloc and free in the standard library set, they are real functions, assert doesn't exist anywhere in the standard library set. Okay? Assert was just this quick and dirty macro that was defined in assert.h. Okay? Make sense? Okay. So there's that. If I bring it back, everything is obviously restored. The prototypes, and this I think is a fairly astute way of putting this, the prototypes are really in place so that caller and callee have complete agreement on how everything above the safe PC in the activation record is set up. Does that make sense to people? The prototype only mentions parameters. The parameters are housed by the space in an activation record above the safe PC. Everything below the safe PC is the callee's business. But when I call printf and I jump to printf code, we have to make sure that the callee and the caller are in agreement with how information was stacked at the top portion of an activation record. Because it's just this trust where if I'm calling printf and I lay down a string constant right here and I say take over, printf has to go, oh, I just assumed that there's a string above the safe PC. I hope so because I'm treating it as such. And if it isn't, there are problems. But if it is, it just prints it. Does that make sense? Okay. If I were to do this, let me write another block of code. This is actually a really weird looking program. But this is typical of the type of thing you see in 107. Int main. I actually don't care about argc and argv. I'm going to declare an int. I'm just going to call it num. And I'm going to set it equal to 15. Actually, you know what? I lied. Let me set it equal to 65. And I'm going to do this. Int length is equal to no laughing strlen ampersand of car star ampersand of noom noom. Okay. So I'm calling strlen in this completely bogus way. I want to printf length equals %d \m. I'll just put length down, and I will return 0. And let's, for the moment, not put any prototypes up there. Okay, suppose I completely punt on the pound include section. Compiles this, it's like, that's fine. Oh, I don't like that. I'm seeing a function call I haven't seen a prototype for. But because of the way I'm calling it, I'm going to assume it takes a char star followed by an integer, okay? And I'm going to assume it returns an int, because I always do that for prototypes that I infer information about. The assignment works fine. It prints out whatever length happens to be bound to and then returns. So this, if I were to compile this, it would only issue one warning. Does that make sense? Now that call is totally messed up. I don't know how often you've had to call strlen. You've called like memcopy and strcopy and all that. This just takes normally one argument, which is a string, and returns the number of visible characters before the \0. Does that make sense? Okay. So the way I'm calling this, this is where num resides in memory. I put a 65 there. This is where length resides. Okay. I haven't initialized it yet, but it calls strlen before it can initialize length. So if that's the activation record and it preps for this call right here and it's inferring the prototype, it goes, okay, I don't know what you're doing, but I'm going to do an SP is equal to SP minus 8. I'm going to put the address of num right there. I cast it to be a char star, so it actually it thinks that there are characters right there, 4 of them. Okay? Make sense? It puts a 65 right there. It leaves SP pointing right there. And then it calls strlen. When this generates a .o file, all it has inside that's of interest to the linker is the call to strlen. You may think that during link phase that it's going to freak out because it's going to somehow know that strlen only takes one argument. That is not true. There's no information, there's no direct information inside the .o files about how many parameters something's supposed to take. You can look at the .o file and you can see SP is equal to SP minus 8 versus SP is equal to SP minus 4 versus SP is equal to SP minus 16. You'd have some sense as to how many parameters there are, but not really because it might be one 16-byte struct or 4 4-byte integers. Okay? When it does the linking, it just looks for the name. It doesn't do any checking whatsoever on argument type. I'm sorry, on parameter type. So the fact that this signature is zonked and messed up, it's irrelevant to the link phase. All that it looks for during the link phase is for something that responds to the name strlen, and that's exactly what happens. So when this executes and it jumps to strlen, strlen inherits this picture. This is where a save PC is set up. The real implementation of strlen was written and compiled to only have one char star variable. Does that make sense to people? So its assembly code only goes this high. It may actually decrement this by some other multiple of 4 bytes for its local variables. Okay? It does a for loop inside, really, is what all it does, and then returns it to here. But do you understand why the 65 is more or less ignored? Does that make sense to people? Okay? So as it turns out, this will compile with one warning. If I want to turn off the warning, I can do this. I can actually manually prototype it at the top. That's the type of thing that comes into the translation unit as a result of preprocessing anyway. So if I want to suppress the warning there and just manually prototype because obviously I think that's the prototype because that's the way I'm calling it, then I can just do that. Okay? A lot of times you will see people only include the prototype manually. The alternative is to pound include this big .h file that slows down compilation. And if you're concerned about, if you have to remake a system 75 times a day from scratch, and the number of pound includes actually impacts compilation time, a lot of times you'll just manually prototype things instead of pound including everything. It's a little risky because technically, less egregious but technically incorrect versions of this mistake could actually happen, okay, and cause code to compile that probably shouldn't. But this will now compile cleanly, because I said this line is perfectly good as is. When it runs, it calls Sternland. It only thinks about everything below that little arc right there. Okay? It actually treats that as a car star. It has no choice but to do that. We even coached it to think that it's a car star for the call. It's going to return, it's going to bind length to some value. It's going to print it out. Does anyone have any idea what's going to be printed out by this program? Yeah?
0.
It would be 0 on basically most systems. I'm going to say most. Many systems. It would actually print out 1 on some other systems.
Does it count the null character as 1?
No, it doesn't. It actually doesn't have anything to do with the null character. I'm assuming that the 4-byte integer that really resides here is stored this way. Does that make sense? If that's the way it's set up, then there really is a single byte of 0 all the way to the left. And so as far as this argument is concerned, it actually thinks it's pointing to the empty string in this little static space on the stack. Okay? Makes sense? That is the big endian view. In a little endian system, these would be reversed. Right? And so 65 happens to be a capital A. It doesn't even care that it's 65 so much as it is non-zero. So on little endian systems, this would actually print out length is equal to 1. Okay? Does that make sense? The interesting part is that this is a complete hack. I manually prototyped it right there. You should try not to do that because it allows things like this to happen. It turns out it doesn't cause any problems. I'm sorry, it doesn't cause any runtime problems. It'll actually execute properly. And because this happens to point to either 00065 or 65000, both of those can be interpreted from the beginning of that sequence as some C string. One happens to be the empty string. The other one happens to be the capital A followed by a \0. Okay? It will just have some response, even though it's a little weird. Okay? Make sense? Yep.
So it disregards the second parameter?
The caller does not. The caller actually places it there. But think about the implementation of Sterland was really compiled with the normal prototype, not this one. So it only reaches 4 bytes above, at most 4 bytes above the safe PC, which is why I draw this arc right here. Okay? Does that make sense? This still sits there. It's still popped off the stack when Sterland returns, because this did an SP is equal to SP minus 8. It just assumes that 65 was integral to the implementation or to the execution of Sterland, and it pops it off afterwards. Okay? Does that make sense? It wasn't my exam question. Julie Zonsky gave this like 12 years ago. I couldn't believe it when I read it. I was like, wow, that was really hard. I don't know whether people got it right or not, but I thought it was very interesting. That's why I wanted to put it in lecture. Let me give you the opposite scenario here, though. Suppose I do this. Int memCompare void star v1, and I just mess up. And for whatever reason, I think that somehow memCompare only needs 1 void star. And then I have some block of code that declares an int called n is equal to 17. And I do int m is equal to em cmp ampersand of n. And that's it. That's all I care about. Okay, it's not a very interesting block of code. I just want to see what happens if we call a function with only 1 argument that really expects 3. Okay? You may not remember the real prototype for memCompare. It's used incidentally in assignment 4, but it's kind of like strcomp, except you explicitly pass in the number of bytes that should be compared, since \zeros are meaningless to a memory compare. The actual prototype is this. And this is the way memCompare was compiled behind the scenes. v1 void star v2 int size. That's the real prototype. The call here would declare n, stack it right there with a 17. It would put an m there that has no value yet. when it calls memCompare according to that prototype, there's a safe PC right there. There's the address of n right there, and this is compiled with the idea that only the 4 bytes above the safe PC actually are relevant to the implementation of memCompare. Does that make sense to people? When we transfer execution to the real memCompare that has a completely different idea of what the parameter list looks like, it inherits that as a safe PC, and it's like, wow, I have 12 bytes of information above the safe PC. So it just accesses them. Okay? So this overlays the space for V1. This uninitialized value overlays the space that's used for V2, and it happens to inherit 17 for the size. And it executes according to those 3 values. I'm not saying it's sensible, I'm just telling you what happens. Okay? So because I did that, and because this is the only thing that's part of my main function, it would compile, it would execute, it probably would crash. Okay? It's probably the case because this is uninitialized, so it's very unlikely that it has as a random 4-byte address inside of that points to something that's really part of the stack or the heap or the code segment. Okay? Does that make sense? If it happens to be that, then it would run somehow. Okay? But it probably would not. You guys getting what's going on here? Okay. It's C as a language, it's very easy to get something to compile. And it sounds like, I mean, you may not believe that, but if coming from C++ land in 106B, maybe you do realize it now. You're certainly seeing things compile in assignments 3 and assignments 4 that are wrong. Okay, they just crash or they don't work. If it were a fully, strongly typed system where there was no idea of exposed pointer or void star or casting, you'd have to actually get a lot more things right before things compiled. Does that make sense? You're used to templates from C++, and you don't use any generics with void stars in C++. You just usually don't. Even though it's a pain to get things to compile in C++, it's rarely the case that you crash. Okay? To the extent that you use templates, and template containers in C++, you're that much less likely to deal with pointers, and so you just don't see as many crashes when you run a C++ program. Okay? You do see a lot of crashes with C programs. We all believe that now. Okay? It's almost like C++ as a language. The compiler is like this hyper persnickety wedding planner where everything has to be in place before it'll let the wedding happen. Okay? Does that make sense? Language like C, it's like it'll all work out. As that's what the wedding planner is saying. It's like, yeah, it's a void star, it's a void star. Yep, as long as you know what's going on, I trust it'll all execute. And if it doesn't, well, then that's your problem. Okay, it's really what the C compiler is viewing it as. This is definitely a C compiler exploit right here. You couldn't do something like this in the pure C++ extensions of the C language. Okay? Does that make sense? Do you know how you can overload functions in C++? You can actually define a function with the same name as long as it has different parameter types. You can even have the same number of parameters as long as it can disambiguate between 2 different versions based on the signatures of the the 2 calls and the data types of the call. It'll let you define one. You can't do that in pure C. If I have memcmp as a function name, then I can only use it once. What C++ does, it's very clever. When it compiles it, it actually doesn't tag the first instruction of a function with just the name of the function. It actually uses the name of the function and the data types in the order they're presented on the argument list to assemble a more complicated function symbol. So something like this in C++ would be a call to memcmp. I'll write it this way. This is the way it would be set up in pure C. In C++, it has to be able to disambiguate between multiple versions of memcomp with different signatures. So it actually does this. And I'm making this part up. But something along those lines. Okay? Does that make sense? So if you were to compile this with a C++ compiler and you were to compile that implementation with a C++ compiler, this would be a call to memcompare underscore void star underscore p, whereas this would be tagged with memcompare underscore void underscore p underscore void underscore p underscore int. Does that make sense? you might as well call the functions x and y as far as the C++ compiler is concerned. Okay, so a call to this from a C++ .o file to this would lead to linking problems. Okay, does that make sense to people? Yes, no? So C++ is a little safer in that regard as well. Okay, so there's that. I have a few things I want to do. I'm going to spend today and Friday easing up a little bit before I've actually formally covered everything that I'm going to cover on the midterm. In fact, I'm not even going to test you on this stuff on the midterm. I'm just trying to give you a very big picture of what the entire effort is into building a C or C++ executable. I want to go back a little bit and talk about debugging, and in particular give you some lighthearted examples as to why programs crash the way they do. It's one thing to say they crashed. That's not very interesting and insightful. Yeah, it crashed. Well, of course it did. It's C. But why did it crash? It's like, why did it crash, and what happened at runtime to actually prompt the crash or the segmentation fault or the bus error? I know you have no idea what the difference between those two is. I'll tell you right now what they are. But I just want to show you why programs run the way they do when there are little bugs in there. Okay, and even though something survives compilation and survives linking, why it runs, it can still go astray. Let me quickly talk about the two very harsh alerts that are thrown when your program crashes. You're used to seeing segmentation faults, and you're used to seeing bus errors. Okay, you've probably seen seg faults more recent in assignments 3 and assignment 4 more. I wouldn't be surprised if you saw a lot of bus errors in assignment 2. Okay, this right here always comes into place when you dereference a bad pointer. That turns out to be the case with this as well, but there's different reasons in each scenario. If you ever try to dereference the null pointer, if you really try to do this, well, that wouldn't compile because you can't dereference a void star. But conceptually, if you were to actually try and jump to the null address to discover an integer or a char star, it issues a segmentation fault. Okay? The reason that's the case is because for the 12th time this quarter, I'm drawing all of RAM, and I'm drawing the stack up here, and I'm drawing the heap right here. Stack, heap. Here's the code segment. There's also the data segment is usually actually down here, but I'll draw it up here because there's room. The null address corresponds to that. Do you understand that the 4 bytes at address 0, 1, 2, and 3, they're not part of any segment? Okay? The operating system can tell that. It's like, okay, you're dereferencing the null pointer. I'm not mapping the 0 address to your stack or your heap or your code segment. So I know this can't possibly be right because you're not dealing with an address that should be under your jurisdiction. It's not the address of a local variable. It wasn't an address that was handed back from malloc. So why are you dereferencing it? I'm going to scream at you in the form of a seg fault. Okay, and that's what a segmentation fault is. It's your fault for not mapping to a segment. Okay, this is a little bit different. Bus errors are actually generated when you dereference an address that really is somewhere in one of the 4 segments, but it can tell, or it thinks it can tell, that the address couldn't possibly correspond to what you think it is. If you have an arbitrary address here, void star, and VP is equal to whatever it's equal to, and then you do this. If VP really is an address that corresponds to that resides somewhere on one of the 4 segments, you will not get a segmentation fault because you are hitting a segment. Because it wants to make things simpler, compilers adhere to what's called adhere to a restriction that's imposed by the hardware in the operating system that all integers actually begin at addresses that are a multiple of 4. That all shorts begin at even addresses. There's no restriction on characters, but basically just to keep things clean and to kind of optimize the hardware, it always assumes that all figures other than shorts and bytes reside at addresses that are a multiple of 4. I don't know whether you questioned why I had this random padding every once in a while in the data images from assignment 2. Like I said, okay, and there's a 2-byte short that follows this \0, unless the name of the actor is even, in which case there's 2 \0s. That's because I knew you wanted to dereference some pointer in there as a short star. And if it happened to be an odd address, even though the 2 bytes that are there really do pack in a short, the hardware will be like, ooh, bus error. I don't like that. I don't like you dereferencing odd addresses. And thinking that there are shorts there, because I know that the compiler would never normally put a short at an odd base address. Does that make sense to people? Okay. If I do this, and so let's say that this right here, if VP is equally likely to be any address that's inside a stack, the stack or the heap or the data segment or the code segment, then this would throw a bus error with 50% probability. Does that make sense? Okay. If it doesn't throw a bus error, then it really does write a 2-byte 7 somewhere. If I were to do this, then that would throw a bus error if VP was really part of some segment somewhere, but VP wasn't a multiple of 4. The address 2002, no, it wouldn't put an int there, right? So it's not going to let you start laying down a 4-byte integer at what feels like an odd address, even though it's not really odd. Address 2000 is fine. Address 2004 and 2008, they're great. 2002, no. 2001, doubly no. Okay, all of those intervening addresses could not house or be the base address of an integer. It's like a block where all the houses have to begin with, like, have to be a multiple of 4 in address. Okay, or one of those snobby neighborhoods where everything's like 100 or 200. Okay, on the addresses on the houses. Does that make sense to people? Okay. So when you see a bus error, when you see a seg fault, it's almost always because you have some null pointer. In theory, it can be any address off of a segment, but it's going to be that you're either dereferencing null or 4 or 8 or some very small null pointer relative address. Okay. Bus errors I see less often. It only usually happens when you're dealing with manually packed data, like we saw in assignment 2, and you're trying to rehydrate 2-byte and 4-byte figures from arbitrary addresses internal to some data image. Okay? Okay. What I want to do now is, now that you have that, you have some more information. When you see bus errors and seg faults, at least you have some idea what's happening. Let me throw some code up on the board. And I want you to understand why this program does what it does. Here is the entire program. I'm not going to concern myself with pound includes. Just assume anything that needs to be pound include is. And I'm going to declare an int I right there. I'm going to declare an int array of length 4 below it. And then I'm going to deliberately mess up. I is equal to 0. I less than, is it less than or equal to? I don't know. Let me include more. That's probably safer. And I'm going to do array of I is equal to 0. Okay? You see the bug. Okay? You see that it's overflowing the bounds of the array. What you may not be sensitive to, and this is something you can only understand after you see a mock memory model, which is actually really close to the real memory model of most function call and return mechanisms, is that this code executes with this image in mind. Here's the save PC of whoever called main. It's actually a function called start that calls main, and start's responsibility is to parse the command line to build the argv array of strings, count the number of strings that are there, put that number in argc. It actually puts a null after the very last string. So in case you want to ignore argc, you can. But then this is that array of length 4. This is I. And let me just be obtuse about it and just trace through this, even though you know exactly how it's going to run. It's going to set this equal to 0. It's going to pass the test. It's going to put a 0 right there. It's going to come around and promote that to a 1. It's going to pass the test. So it actually lays a 0 right there. It succeeds in making this 2 and then 3 and intermittently getting that right there. After it writes that 0, it promotes this to a 4. Okay, and you're like, okay, something's going to happen, and it's probably not good. Comes over here, it passes this test, So it says, okay, I guess, it's not even going to say I guess. It just does it. It's not suspicious. It comes over here and it writes a 0 to something that's 4 integers above the base address of array. So where does it write that 0? Over the 4. So it just does that. It comes back up here, and it's like, wow, that's weird. I thought I saw a 4 here before, but I guess it was a 0. So I'm going to promote it to a 1. And I'm just going to write a 0 over here. Wow, it's a 0 already. What a coincidence. And it's going to keep on doing this, okay? And it's going to basically start right there, go up here, and it's going to keep on cycling here. How long? Forever. Okay? And that's because of the way that everything happens to be packed in memory, that this buffer overflow, technically that's what it is, really does damage. It doesn't actually, it kills data. In this case, it happens to get a program to run forever. So this is a slightly more complicated version of while true. Okay? Does that make sense to people? Okay. There are other variations on that. Let me just do a couple other things here. Let me just assume I have to change this one line here, so I'll give you a second to recover. Suppose I just do this. Short array. So the picture, the stack frame picture actually changes a little bit. Now the stack picture looks like this. I is still this big fat int, but now there are 4 shorts packed here. Okay? Make sense? On some systems, this is going to work fine. Fine being a relative term, and meaning not badly. And in some other systems, it's going to run forever. Okay? For very much the same reasons, except that there's a little bit of a size indifference thing here that we have to worry about. This is set to 0, lays a 0 down there. This is set to 1, lays a 0 down there. This is set to a big fat 2, lays a 0 there. 3, puts a 0 right there. Then this thing is promoted to a 4. I'll put it right there. Let's say it's a big endian system. Okay? So it's really dot, to dot, to dot, right there. So if it's a big endian system, when it overwrites the bounds of the array, all it's doing is it's overlaying zeros where zeros already were. So I'm not saying it's correct, but you actually don't see the problem, and it just runs, and it takes 20% longer than it should have, but you don't deal with things that fast, so you don't really care. And it runs, and it returns, and you think all is great. And so you move from the alanes, and it's 11:59, you're like, oh, I better test it on the pods. So you bring it over here, and you're like, wow, it runs forever. Why? Okay? That's because the 4 was over here on the little endian systems, and the pods run Linux on x86 machines. They're little endian. It writes this 4, overwrites this 40, a 2-byte representation in little endian form of a 4 with 00, which is 0 in both big endian and little endian, and then goes through the same confuse cycle that the int array version did. Does that make sense to people? Okay. So there's that. I have 1 minute. Let me just give you one other example. I have 1 minute and 20 seconds. I can do it. I actually gave this about 5 years ago on a midterm. I thought it was so clever, and they didn't. So, I had this as a function. Void foo. And I was curious as to what happens when you call foo. I did this int array of size 4, int I, and then I did this. Don't question why I'm doing it. I less than or equal to 4. The error is the same. The for loop issue is exactly the same. But I do this. And the fact that array is not initialized, well, that's a weird thing to do to an uninitialized array slot. Okay? Notice that the array is above I this time. Okay? So I'm back with all integers. There's my I variable. Here are the 4 integers that are part of a larger array. Okay? And so it does this, and all it does here, this goes from 0 up through 4. It just demotes this by 4, whatever happens to be in there. And because it's allowed to go one iteration too many, right? Whatever happens to be here is also decremented by 4. Now we know whatever happens to be there. If that's the only set of local variables that I declare, this is the saved PC. Okay? That makes sense to people? So the saved PC, without really knowing, somebody took the saved PC and decremented it by 4, numerically by 4. What that means is that this is a pointer which used to point to the instruction after call to foo, something that lets it continue. Somebody said, I'm going to make you unhappy and put you right there. The impact is that this thing returns and the callee wakes up and execution carries forth where the safe PC says it should carry forth from. Somebody moved the piece of popcorn back 4 feet. And so it says, oh, I have to call foo again. And it does. And it returns like, oh, I have to call foo again. Okay, and that's exactly what happens. It keeps putting the address of this thing down here, but because of this buffer overflow, it actually keeps decrementing the safe PC back 4 bytes, which means it marches it back 1 instruction, so how you get this more interesting version of infinite. It kind of is infinite recursion. Right at the end of the foo call, really toward the end of the foo call, it calls foo again. Okay, does that make sense? Okay, so come Friday, I will talk to you about printf and a couple other things, and I will talk about, that's probably it. I'll probably be a nice, easy lecture on Friday. Have a good night.